you're all doing well. So today I wanted to just finish off some stuff about the vector potential, namely the multipole expansion, but really on the agenda originally, at the very beginning of the course was to really talk about magnetostatics in matter at this stage, but we haven't yet done electrostatics in matter, and that's going to be the subject of today. So as compared to the kind of original plan, we're like one lecture behind. We'll try to keep it at that, but let's see how we do. So if you don't mind, I'll just jump straight into it because we need to make quite a lot of progress. The little stuff about the multipole expansion is not going to be too long because there's essentially one result that I want to show you that is going to be also useful when we talk about magnetostatics in the presence of matter. Okay, so without further ado, I'm just going to jump straight into the continuation of what we were doing last time. So you'll remember that we had discussed gauge choices for the vector potential. We had some expression for the vector potential, which involved some integral over space of the current density. So we had a completely generic expression where our vector potential was given as a volume integral of some volume current density with the usual factor of 1 over distance that we're accustomed to. Today, I'm just going to start with a slightly simpler setup, which is a simple wire. I imagine that I've got a closed loop of a shape which is indeterminate at this stage, carrying some current I. And the expression for the vector potential for this object is then given by the line integral along this loop of this current vector that we have here, divided by the distance. Okay, so in general, this is quite nasty. This is quite complicated because the loops we're interested in, they can take arbitrary shapes. However, we've seen a great big trick for the approximation of the potential in the electrostatic case, which we can apply here as well, namely the multipole expansion. And here, in a sense, it's even simpler than what we had for the electrostatic case. So let's just see how that looks. So I remind you that the general idea is that we will just replace the 1 over r minus r prime by this expansion that we had given. It's a completely generic expansion that we had here, where we had a development in increasing powers of 1 over the distance. And you remember the summation was from L is equal to 0 all the way to infinity. And we had increasing powers of R over R. R, let me just write it here. So R prime over R to the power L. And then we had the PL, so the Legendre polynomial of cos theta, where theta was the angle between the R and the R prime vectors. And the way we write this is really just the in product of the hat unit vectors in the R and the R prime direction. Okay, so that's just like a mathematical identity that we exploited. And we had tabulated forms for these Legendre polynomials, etc. So here we can actually do absolutely exactly the same thing here using this expression for the vector potential that we had here. So what does this tell us? It tells us that this vector potential A at R just becomes a summation of lots of different terms. So let's just go how it is. In the current loop here, the current is going to be constant along the loop. So the kind of vector direction here, I mean, if I just look at the norm of this vector here, it's always I mu 0 I over 4 pi. And now what am I doing? So I've got a great collection of terms here. Let's do the L is equal to 0 term, the simplest thing. So this is just 1 over R. And now I've got an integral over this closed path of the displacement vector dl prime. Okay, that's the first thing. So I'm just walking along the loop. I'm doing a closed path integral over this loop here. That's the first term. The second term, well, I've got 1 over r squared. I'm now still doing the integral over the closed path p. But now really what I have is some dl prime here, which is my displacement along this thing. And then here I can write it in lots of different ways. So, you know, this can be like really the r prime dotted into r hat, say, okay, plus higher order terms like this. Now let's just see what this this thing is. Well, the nice friendly thing about this first integral here, this one, it's that it's just zero because it's a closed loop. Okay, so there is no monopole term in the vector potential. Okay, and this is related to all the stuff that we've demonstrated about the magnetic field. You remember that the divergence of B is always equal to zero. There's no magnetic charge. And if there was a magnetic charge, we could have a non-zero monopole term, but there's no magnetic charge. So therefore, the monopole term always vanishes. The leading term in the expansion of any vector potential magnetic field is going to be a dipole term. Okay, so so that's the other. And as usual, we've got quadruple terms and whatnot that we're not going to discuss, you know, very extensively. Okay, so but let's just take a few minutes to discuss this dipole term here. And let's look a little bit at how it looks. Okay, so I've got the vector potential A dipole term at R, which is now given by this like slightly complicated integral, mu 0 I over 4 pi, 1 over r squared. And now the integral over my path, dl prime of just my, well, let me just write it as r hat dotted into r prime. Okay, so here, in principle, you can carry out this this integral in any particular case that you have, but there is actually a massive simplification that comes from a little integral identity that is explicited in the online notes. Okay, so I'm actually going to quote it because its derivation would take like 15 minutes, but it's you'll see the end result of it is readily interpretable. Okay, so there's, let me just write it down. There's a handy identity. Namely, let's say, yeah, just give myself some space. Let's say that I've got a certain surface here, which is encompassed by this loop that I'm actually integrating over, okay? Then the integral that we've got listed here, so let's just, maybe I'll just quote it and then interpret it after. So what's the quote? The quote is that the integral over a closed path of this displacement of an arbitrary vector C. So this is arbitrary vector. And here I'm integrating over the, you know, R variable itself. This is equal to a very convenient to interpret thing, which is this, where A is like the surface average of the normal vector on this surface. Okay, so A is by definition the integral over the surface defined by the path P of the normal vector dA. Okay, so just imagine that you give me the path P. I can take any surface that I want. It can be the flattest surface there is. It could actually be the, you know, kind of like shell-like, wavy-like surface if you wanted to. If I integrate over all the surface, the normal elements A, I get kind of a vector that is like the average normal vector on this surface. Yeah. So here I would integrate the, so my DL would be like this. And then I would choose a certain origin. And my R, so let's say that this is my origin, then my R vector would be the position of this DL, right? So this would now be the vector R that I'm integrating over. Okay, so to visualize it, I mean, you got to choose your origin somewhere, but it doesn't actually matter. And the idea is that for any given vector C, which I haven't drawn here, but let's just imagine that you've got some C vector going some way, maybe this is C. Then if you were to, I think you have to try to visualize it a little bit. If I take the in product between, so for every little piece that I'm integrating over here, there's an R. This R itself has an in product with my arbitrary vector C, okay? And I just integrate throughout the loop the in product between that R and that C, okay? So there are, let's say we do a simple case first. So imagine that I have my origin and I'm going to integrate over a circle that's like on the sphere that I would do away from R. Okay, so I'm always at the same radius and I'm doing a circle like this. So on that little circle, my DL is always like this. It goes like this as I go around. My R is like this. Okay, so if you want my R and my DL, they're always perpendicular. I get 0. Okay, and what I'm telling you is that this whole integral here is equivalent to taking your surface and telling me for that surface, here's my average normal vector. It goes that way. Okay, and indeed, if I've got a circle like this, then my average normal vector just goes like this. Okay, and now that's the point. Yeah. So if I was to choose, say, this vector also to be coming from the origin to the center of that circle, then there would be no cross product between the two because the two vectors are parallel. I would need to kind of tilt my surface in order to gain a non-zero result. Okay, so for this, like I say, the proof of this statement is not enlightening. And I invite you to look at it because it's the absolutely general statement. See the lecture notes online. You'll see the proof of this. The proof of it is not enlightening, but the interpretation of it, you'll see, is quite easy and enlightening when we'll get to it in a second. Okay, so you can just look at it. There is absolutely no way that I would ask you for the proof of that thing in an exam or something like that. Okay, so once again, it's a result that you'll probably use once in your life to prove that particular thing for this this particular vector potential. Okay, so I'm really just quoting this result. But let's just do a couple more steps and then interpret what we get. So our A dipole I can rewrite as something better, because now I'm just going to quote this this result here. And what I'm doing here, I'm integrating over this this R prime. So you see, I'm going to choose the C to be proportional to the R. I'm going to just plug that back into the thing. So what I'm doing here is that I'm saying that the vector C that I put in the proof is really just the R hat vector. Okay, and then I'm quoting that thing here. So what this allows me to do is to rewrite the dipole term in a much simpler form. It allows me to rewrite the dipole term as the following thing. So mu0 over 4 pi. And now I'll define an object M, which is a vector that I'll explicit in a second. Okay. For this M, by definition, is going to be I times the integral over my surface of the area encompassed by the loop. Okay, so by notation we call that I times A, and this is known as the magnetic dipole moment. Okay, so what are we saying? We're saying that you've got a certain shape of a loop like this that defines a certain surface that has a certain area for which you have an average normal vector A. Okay? And irrespective of the shape of the loop, if the wire here carries current I, then the strength of the magnetic field that comes out of that, which has this dipole form, is proportional to the area of the loop. Okay, it's a little magical identity that comes from this. You've got your loop. It's oriented in a certain way, given by the average normal vector, and that is your magnetic dipole. If you change the shape of the loop, but you don't change the area of the loop, you're not going to see any difference in the magnetic field that comes out of that. The first order, because here we're once again doing this expansion in 1 over distance. Okay, so this is the kind of statement here. As in the case of the electrostatic field, we had this expansion and increasing powers of 1 over r that extracted important characteristics of the charge distribution. First, the monopole term, the average kind of integrated charge. Then this dipole term, which was the sum of all the little dipoles you could have in there. So here it's exactly the same thing, except that now this dipole is a magnetic dipole. Okay, and again here we can fulfill the if B is equal to 0 condition, because a magnetic dipole you can actually visualize, if you want, as a positive and a negative magnetic charge that are distanced from each other with a little a tiny bit. Okay, that you forget about magnetic charge conservation just on that local level, but that gives you a configuration which is, you know, corresponding to this one here. But really, the physical origin of a magnetic dipole is like a current loop. Okay, so there's no problem with magnetic charge in that case. You would imagine, for example, atoms with circulating, you know, electrons around them to have magnetic dipole moments associated to them. So that's the kind of general formula that's that you can look at for these effects of magnetism. So later on, when we'll talk about stuff in matter, we will go back to this kind of notion of these local dipole moments in there as the leading terms in whatever distribution of currents you might have at a certain distance. What does your magnetic field look like? Okay, so that's just like a statement here. Have you seen these magnetic dipole moments in your first course? You might have just glanced at them very briefly, but I don't think you'll have done anything with them, right? Okay. So the kind of traditional, so here what I'm giving you is the kind of once and for all mathematical proof that this is the proper formula for the dipole in many books. So for example, in Purcell-Morin, there's a really good section where he talks about the kind of beginnings of the multipole expansion for the magnetic field. Actually, I can maybe give you this section here somewhere. And what he does actually is that he considers a particular configuration. Yeah, maybe I can quote it later. I'll have to find it again. But he does a particular configuration. So he's got like a wire with 4 branches like this, and then he computes the magnetic field, takes the leading 1 over r expansion. This is also fine to see at first, but this is the kind of really radically solid, unique derivation that you need for an arbitrary loop, irrespective of its shape. Okay, just at the price of quoting this result that you have to maybe convince yourself of separately. Okay, but that's the idea. So most of the magnetic fields that we'll be dealing with when we deal with matter, we're just going to cut to the dipole form, which is going to be given by this thing. So it's really just this dipole moment crossed into the, 1 over r squared times r vector. Okay. So we'll get back to these things later. Okay.